Do you only film us now and not the 9 o'clock class? Because we're more interested.
We didn't watch this video. We didn't watch this video.
Okay, any other questions?
When are we getting all of it back?
I have to get them back on Monday. Sorry, this week was crazy. Of course, every week is crazy. Yeah, hopefully on Monday, if I can do it after I could put my kids to bed and before I fall asleep on tonight or tomorrow night. Okay, but I have started creating them at least. Okay, so what are we doing? What are we doing? Somebody tell me what we're doing. What's the idea? There's sort of like a story involved, right? Where are we in the story? Transition matrices, right? So you've got this matrix that will take you from one place to another, right? What's the first place? Well, it's taking you from a basis, right? So you've got an abstract vector space. Where actually, for us, we've just got Euclidean. You've got Euclidean vector space. You've got 2 new bases on it, right? So you've got your normal bases, right? The standard basis 1, 0, 0, 0, 1, 0, etc., etc. But you've also got, suppose you have some other bases, right? And you want to change your coordinate system to, from one basis to another basis, right? So remember the story, right? Like, you have your vector space. You have a basis. So if you have a vector in your space, then it's associated with a coordinate vector, right? What's a coordinate vector? What's a coordinate vector?
Coefficient.
The coefficients of the unique linear combination that gives you that vector, right? So everybody has to get this, otherwise we can't go anywhere. Okay. Have your vector. It's associated with a coordinate vector. What's the coordinate vector? It's the coefficients of the unique linear combination of basis elements that give you back your original vector. Right? You take your vector, you express it as a linear combination, you take those coefficients, you peel them off and put them in a vector, and that's your coordinate vector. Okay. You do that, you do that with one basis, and you do that with another basis, right? You do that with another basis, and you get a different coordinate vector. Right? And what we said last time is that there is a matrix that gets you from one coordinate vector to the other coordinate vector, and that is called the change of basis matrix, or the transition matrix. Okay, that's where we were last time, so I hope everybody's all right with that. We did an example of it, which was that we started off with recall this example, we started off with 3, 2, 5, and we wanted to express it in terms of these 3 other vectors, u1, u2, and u3, right? And so we said, oh, look, what we needed to do was to take u1, u2, and u3, put them as the columns of some matrix, right? And then just solve this, right? Just solve this for ABC, right? Solve for ABC. Solve for ABC, and that gives you right, the A, B, and C for which 3, 2, 5 equals A u1 plus B u2 plus C u3, right? Right. So it gives you the coordinate vector, right? In other words, the coordinate vector. Okay, or like in general, right? In general, right? If you have one basis, if you have a basis B, being B1, B2, B3, and a basis U, being U1, U2, U3, right? Then you know that B1, B2, B3 times the coordinate vector with respect to the B basis is U1, U2, U3 times the coordinate vector of the same vector with respect to the U basis. Right? And so the transition matrix from U to B is just you take the B matrix and invert it and multiply it by the U's. Right? And this is what we saw last time. Okay, so we saw all this last time.
So you invert the one that you're going to.
Right, this will take us from U, right? You see that if we, right, what you see is that, right, so think, right, x with respect to the B basis is this guy times x with respect to the U basis, right? And so what does this matrix do? It takes you from the U's to the B's. Okay, right? To go from U to B, you take the U matrix and multiply by the inverse of the B matrix. Okay. And this is what we saw last time. Yeah, Ethan.
I'm sorry, I'm not sure, like the 375 vector, is that like an example of what you said on the right with the
Yeah, it's an example. The thing about this one is that this is with respect to the standard basis, so our matrix over here is this one, so it's invisible. Right? There's the identity matrix secretly hiding over here. Right? This 325 was our vector expressed with respect to the standard basis.
Right.
So, right, if we want to go from right, if we want to go from the standard basis to the U basis, then we need to multiply on the left by the inverse of the U matrix. Multiply on the left by the inverse of the U matrix. Okay. Anybody confused? Everybody all right? Everybody all right? Any questions? We can take it slow. Any questions? Okay. Okay. Okay, I'm going to do something that I don't normally do, but let me, maybe this will be helpful or maybe not. I don't know. Let's try it. So, what is this transition matrix? What is this transition matrix? It's some matrix. We have B1, B2, B3, inverse, U1, U2, U3. Okay, I'm just going to do it for R3, but this could be for Rn. Okay. And then over here, so this is going to be some matrix, right? This is going to be some matrix. Let's suppose that the matrix looks like this. I'm going to call the columns of that, let's call the columns of that product C1, C2, and C3. Okay, so we're really asking, what are these numbers? What are these numbers, right? We've got the transition matrix. What does it actually mean? Okay, I mean, we know what it means, but I'm going to say it in a slightly different way. Okay, I'm going to say something dumb, which is that, well, this means that U1, U2, U3 equals B1, B2, B1, B2, B3 times C1, C2, C3. So what I want you to think about is, what is this first column here? So I'm just going to call it alpha, beta, gamma. What does this first column tell you? I don't know if anybody's going to get this, but if you do, I'll be impressed. Mariah.
Yeah, they're just like the coefficients for B to get to U.
Yeah, the coefficients to combine the b's to get to u, right? In other words, u1 is alpha b1 plus beta b2 plus gamma b3. Exactly. Right? If C2 is going to be maybe I should call these guys. Maybe I'll use the normal guys. So C11, C21, C31, C12, C13, C22, C23, C32, C33. Okay. So we see that this is C11 plus C21 plus C31, right? U2 is going to be C12 B1 plus C22 B2 plus C23 B3. U3 is going to be C31 B1 plus C32 B2 plus C33 B3. Right? In other words, what is the transition matrix? It's what you get if you express the matrix you're coming from, the basis you're coming from. Yeah, you have something else? Oh yeah, thank you. This should be 1, 3. 1, 3, 2.
C.
So what is the transition matrix? It's the matrix that you get if you take the matrix, the basis that you're coming from, and you take the basis that you're going to, and you express the elements of the basis that you're coming from in terms of the basis that you're going to, and then take those coefficients and transpose them, C11, C12, C13, right? C11, C21, C31 are the ones that you use for U1. Okay. Right, so you see, I hope you see it, right? You take the basis you're coming from, express it in terms of the basis you're going to, and then take those coefficients and transpose it, and that's actually the matrix that gets you from the U basis to the V basis. Okay. That's what we see happens in the Euclidean case that we've been dealing with so far. Okay. And so this should give you some explanation of what we did last time. Remember, we did that example and we took the transpose, and everybody's sort of like, well, why are we taking the transpose? Because that's what we want. We need to take the transpose. Okay, so now we're gonna all this was basically to give you some sense of why that transpose occurs. Now I'm going to explain it again in a completely different way. So remember what we're doing. We're doing change of basis for abstract vector spaces. Right? Really, just say vector spaces, but they don't have to be Euclidean vector space. Okay. So you have, right, the vector space of polynomials, or the vector space of matrices, or whatever. Okay. You have some abstract vector space, and you've got two bases for it. Okay, and you know, just as before, you want to go from you want to have some way of getting. You've got two bases. The bases give you coordinate vectors, right? Two coordinate vectors for the same vector, right? Now these coordinate vectors are just numbers, right? These coordinate vectors are in Rn, right? And so we want some way of going from coordinate vector in Rn to the other coordinate vector in Rn, right? And so we'll see that we'll do exactly what we do in the Euclidean case. Okay. So let V be a vector space. Let E be W1 through Wn, and F be V1 through Vn. Both bases of F, V, excuse me. Right. And the question is, how do we get from the coordinate vector with respect to E to the coordinate vector with respect to F? Right. What is our transition matrix? Okay. And we'll take, our cue from what we just did, and we'll say, well, look, we'll express the E basis in terms of the F basis. Right? Express the E basis in terms of the F basis. Right? Express the W's, the WI's, in terms of the VI's. Someday I will fix my notes and make these guys the VI's and those guys the WI's, right? Because E is before F, but V is before W. Sorry. I would do it on the fly now, but I'm worried that I'll make some mistake. So you say, well, okay, W1 can be expressed as some linear combination, S11 V1 plus S21 V2 plus Sn1 Vn. W2 is S12 V1. And you notice I'm using the reverse indices because I'm going to take the transpose later on. S1n V1 plus S2n V2, whoops, V2 plus S n Vn. Okay, so let S be just what you expect, S11, S1n. Let S be the transpose of that. Okay, so take these coefficients, right? Take these coefficients, transpose them, make a matrix out of it. So I claim that S is the matrix that will take us from the E coordinate system to the F coordinate system. Okay. So the way we're going to see this is the following. We're going to abbreviate the system, okay, as follows. So we'll say we abbreviate the set of equations as follows. Well, for the first one, v1, v2, to vn times s1, 1 to sn1 equals w1. Yeah, right.
But can you repeat like the notation about with like the v in square brackets sub e?
This is the coordinate vector of v with respect to the e. With respect to e, this is the set of coefficients that you get from expressing v as a linear combination.
Okay.
Right? This is coefficients you get expressing with a linear combination with respect to the f basis.
Okay.
So what we're saying is that S is the matrix that gets us from one coordinate vector to the other coordinate vector for the same vector. Right? Your vector has two instances, right? Two representations. Okay. Any other questions? Okay. So we're going to abbreviate the first line like this, right? The first line here, right? That's the same thing as saying this, right? Everybody all right with that? This first line, the same thing as saying that, right? S11v1 plus fv2, S21v2 plus da 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 da, Sn1vn equals w1. Okay, so I just abbreviated the first line. I do that for every line. Okay, for every line I create such an abbreviation. So we abbreviate the whole thing. We abbreviate the whole thing like this. W1 through Wn equals V1 through Vn times S11 Sn1 S1n Sn. So this thing here is an abbreviation for all of them together. Okay. Right. Okay. Is everybody all right with that? I just take, I do the sort of abbreviation for each line, and I just put them all together. Right. Right. W1 is going to be, it's going to be that thing on the right. W2 is going to be the next thing, etc., etc., etc. Okay. So it's a little bit sort of not kosher to do this because these guys are not numbers, right? These guys are not numbers. These are vectors. Okay. So this is really like a symbolic thing rather than you don't want to think of this as a matrix. Okay. I mean
It's not.
I mean, it is, but it's more than anything, it's just an abbreviation for this. Okay, right. Like these guys are vectors rather than numbers. I mean, this is a vector, but each element is a vector.
They're like column vectors.
They're not column vectors, right? They're not column vectors. Yeah. So that's why this is not kosher, right? These are elements of your abstract vector space.
Okay. Yeah.
Like this. These if we're
0, 1.
This could be like if we're in PX, say this could be different polynomial. Each guy is a different polynomial. Yeah. So don't. Yeah. This is more of an abbreviation, like a shorthand for this. Okay. So everybody all right? All we've done is taken this thing here, this whole thing here, and abbreviate it as this equality. Okay, so remember our problem, right? We're trying to get from from VE to VF. Why I have not used the second board alternative. Kind of confusing. Okay, yeah, there's a second board here. Why have I not used it? Just. There's actually three, but it's a little bit tricky to use the third board, right? Because you cover it up once you use it, right, which is not ideal. Yeah, okay, so let's go from, the whole class is like, okay, so let's think if the coordinate vector with respect to E is something xn, what is the coordinate vector with respect to F? Okay, let's think. Say, okay, well, the coordinate vector with respect to E being x1 to xn is the same thing as saying that V equals W1 to Wn times x1 to xn. And again, this is an abbreviation for just a linear combination statement. Right? That V is x1 W1 plus x2 W2 plus xn df. Okay. Okay. Everybody okay? Okay. So now let's use the starred equality up there, right? Which is just an abbreviation of this whole system of linear equations. Okay, I'm going to replace W with the thing on the right, V1 to Vn times the S matrix. Okay, but this thing here is, S times this. It's some vector y1 to yn. Right? Oh, yeah. What is this y1 through yn? You see what it is. We've got V equals, V is this linear combination of the VI's. What is this y1 through yn? V is expressed as a linear combination of the VI's with these coefficients. So these coefficients are the
Under the F coordinate.
the what?
F coordinate?
The F coordinates, the coordinates of V with respect to F. Exactly. Right. Coordinates of V with respect to F.
VF, right?
Right. You're saying that VF? I'm sorry. Okay, yeah. The coordinates of V with respect to F. Right? In other words, S times the coordinate vectors with respect to E is the coordinate vectors with respect to F. Right? S, right? This Y was this thing, right? This thing is the coordinate vectors with respect to V, and with the coordinate vectors of V with respect to F. Right? So S is the thing that gets us from the VE to the VF. S is the thing that gets us from VE to VF. VF is S times VE. Okay. Okay. So that's why what we did last time actually worked. Okay. I know that was maybe not the easiest thing. Any questions? Right. 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 You say, right, we want right? We have VE, and we want VF. Well, VE is the coordinates that we use to express V as a linear combination of the W's, right? This is VE right here. This guy here is VE. Right? It's the coefficients that we use to express V as a linear combination of the W's. We want the coefficients that express V as a linear combination of the V's. Okay, and so what we do is we take the W's and use this relation. The W's can be expressed in terms of the V's. Right? The W's can be expressed in terms of the V's, and so we do it. Right? We say, we're going to switch these guys out for this. They are this times this matrix. Right? And so what, but by associativity, right, this thing here is some other matrix, some other vector, and you see that that's those. So then we've got V expressed as a linear combination of V's, of the VI's, right? And so we've got the new coordinates. In other words, S was our change of basis matrix.
So would V1 Vn technically be like, so we have the equation, the change, so V sub, so you had the equation x sub b equals the inverse of b1 dot dot bn, and then times u1 dot dot un times x, like the change base to u.
Yeah.
So like in this case, would v1 bn be the inverse?
The trouble is that these guys are not numbers anymore.
Okay.
Right? So we can't do that. We can't do what we did in the previous use, right? We can't say, oh yeah, put these guys in a matrix, and then take their inverse, and then multiply by the other basis, by the matrix of the other vectors, right? Because what does it mean? You take 1x squared and then invert it. What's the inverse of this? We can't do it.
Yeah. Okay.
We can't do it that way. Okay. But it turns out that we basically do almost exactly the same thing.
Okay.
We do something analogous.
Okay.
We can't do that. Mm-hmm. But we can create the matrix expressing the U guys in terms of the B guys.
Okay.
Right? And that's what we do, and we use that matrix.
Okay.
But isn't it difficult to get that matrix if we don't create an inverse and then multiply them?
Well, yeah. So we had this example last time. Do you remember? We said going from let one basis of P2, P3 be this, let another basis be this.
Yeah. It could get more complicated.
It could get more complicated.
Yeah.
It's true, right? So you'd have to do more work, but yeah. So you'd have to express each of these guys. Express these guys in terms of these guys, and then take the transpose of the coefficients, and then that would be your matrix. One easy one in this example only, or in this sort of example, you can actually do the opposite. It's easier to express these guys in terms of those guys, right? That would give you the transition matrix from U to B. From B to U, right? From B to U. And then you take the inverse of that, and that would give you the one that you're looking for. So you could do it that way. It's a way of making it a little easier. Yeah, you
So all we necessarily need to take away from this is, I understand how we got there.
Yeah.
We just need to find that necessarily the S matrix using.
Yeah. In terms of actually doing it,
right.
All you need to do is express the matrix that the basis that you're coming from to the matrix that in terms of the basis that you're going to, and then take the transpose of those coefficients, and that'll be your transition matrix. That's it.
Where in this explanation are you going to transpose of the S matrix?
Right here. Right here. right here, going from here to here. Take a look. Right? S1, these guys turn out to be the first column of my matrix.
Oh, okay.
Right? So that's the transpose. That's why those guys become the, that's why you transpose that. The first row, the coefficients from the first row become the first coefficients in the first column, the entries of the first column of your transition matrix. And so on and so forth. Okay, let me go on. Observations about transition matrices. First off is that they're invertible. Sort of basically alluded to already. Why does it happen? If you think S takes the coefficients with respect to the E basis and gives you the coefficients with respect to the F basis, when could S of something be 0? When could S of something be 0? That would mean that the coefficients with respect to the F basis are all 0. So what's your vector? The 0 vector, right? Right? That means that your V is the 0 vector. If your V is the 0 vector, what's its coefficients with respect to the E basis? All zeros, right? Again, right? When could this happen? Only if the V vector is the 0 vector. But then VE must also be 0, the 0 vector, right? In other words, X would have to be the 0 vector, right? So the only time S of X is 0 is if X is 0. In other words, S is invertible. S is invertible. Switch the boards. Okay. Second observation, if S is invertible, then S is a transition matrix. And this is sort of a hokey thing to say, but it's true, but it's kind of a weird thing to say. If S is invertible, then you can use it as a transition matrix between two bases. Okay, so it's kind of a weird thing to do, but say, okay, well, why? Let V1 to Vn be some basis, be a basis of some space. Some vector space. Okay. Then construct W1 to Wn by taking linear combinations of the V's. Okay, so you basically you make up a second basis. Okay, you make up a second basis so that S is its transition matrix. Okay. This is kind of a bizarre thing to do. Okay, in fact, I didn't even mention this in the first class because it's so bizarre. Okay. But we have a couple minutes, I'll tell you guys. So you say, okay, I'm gonna choose I choose an arbitrary basis. I choose some basis in some space, and then I make up a second basis. Okay, I make a second set of vectors. I don't know it's a basis yet. We need to show that's a basis. Okay, but if I can show that the second thing's a basis, well then this is the transition matrix between those bases by construction, right? I made this thing so that this is the transition matrix. Yeah, so.
When did you ever use this?
Yeah.
Oh, okay.
Yeah. But since I started it, let me finish it. Okay, so then my construction, if the WIs are a basis, then S is by construction the transition matrix from the V's to the W's. Okay, because we made it that way. Okay. So the only thing we need to show is that these guys are a basis. So it suffices to show that these guys are linearly independent. Because they're the right size, right? There are n of them, there are n of the other guys. So we only need to show linear independence. Okay, so when could W1 be Wn, x1 to xn be the zero vector, right? We need to see that all the xi's will see all xi must be zero. Right? The only way to get the zero vector is if all the coefficients are zero. Right? We'll see that these guys are linearly independent. Well, again, this is the same thing as saying that v1 through vn times s times x1 through xn equals 0. Right? From this. Right, we replace the w's with the v times s. Okay. This again is some like y1 through yn. Right? So this is equal to 0 if and only if this is equal to 0. Right? But the VI's are independent. Right? The VI's were a basis. So what do we know about the YI's? VI's times this is equal to 0. So the Y's must be all 0. They must be all 0. Right? So by independence, of the VI's, all the yi are equal to 0. Right? But that means that S times x1 through xn equals the 0 vector. Okay. But S was an invertible matrix. So what do we know about the xi's?
They're 0.
They're all zeros, right? Since S is invertible, all the xi's are 0. Right? And so we have linear independence of the w's. It's useless, but kind of cool. Okay. And the point is this, that what we see is that if you're a transition matrix, then you're invertible. If you're invertible, you're a transition matrix. Okay. So all invertible matrices you can think of as transition matrices. Right? the set of transition matrices is exactly the set of invertible matrices. So it's just another viewpoint, if not a very useful one. Okay, that's it for today.